The broadcast is now starting. All attendees are in listen-only mode.
Good morning and good afternoon. This is Mark Kovich. I'm a system sales specialist for IBM. I am part of the IBM Internet of Things continuous engineering organization, now called Connected Products. Thank you for joining the webinar today. Subject matter is going to be design patterns for embedded systems in C. Today presenting is Dr. Bruce Douglas. He is a chief evangelist at IBM. Before we get started, I'd like to mention that you're in listen mode only and that this webinar is being recorded. We'll have a question and answer session at the end of Bruce's presentation. I'd like to point out the question box in your control panel there. This is plus mark, says questions. Just click on that, it'll expand. You can actually drag that portion of the screen or the dialog box across your desktop if you want to expand it further. When you submit a question, you can do that at any time during the presentation. I'll keep it in the queue and I'll read it to Bruce if Bruce takes a pause, or we'll do it at the end of Bruce's presentation. So just be aware that it may be a number of minutes before we actually get to the question, but I'll communicate with you through that dialog box and let you know when the question is coming up. Also, the presentation that Bruce is utilizing today is available right now. It's in the handout section of the GoToWebinar control panel. Just click on that plus sign. It'll expand, and you can download the presentation directly during the webinar. If you don't do it or you're having difficulty with that functionality, just look for my automated email that I send to all registrants and attendees of the webinars. And in that follow-up email will be a link where we're now archiving all the current webinars. That includes the presentation and the recording, or just feel free to reply to me if you have any further questions or interest. Also, I'd like to mention that we're hoping to get all the webinars loaded into this new site. We're uploading about 3 per day, and I'm hoping over the next several weeks we'll have the entire series of the past 4 years of webinars into that new system. So feel free to copy and paste the link that's in the email, and also I'll send you the link in the chat window. So if you want to do that now, you can go ahead and copy and paste it into your web browser. So with that said, I think that pretty much takes care of the logistics, and I'm going to pass it off to Bruce. Bruce, you can start the presentation.
All right, thanks, Mark. And welcome, everybody, to this discussion of design patterns. So design patterns are ways of organizing systems to optimize certain properties of the system. And if you look at design patterns, if you go to Google, design patterns, you get a bunch of hits, like on the order of 4 or 5 million hits last time I did it. So there are a lot of design patterns out there to achieve different kinds of purposes. Where I focus more on embedded real-time systems and embedded real-time software. And so those patterns are of particular interest to me, and that's what's going to be the focus of this discussion. Some of these patterns, we'll talk about some specific patterns, but there's a bunch of patterns. I teach a week-long course on this topic. I've written books on this topic. I've published papers on this topic, and of course, webcasts. So there's a lot of information out there for those who are interested in pursuing this further. So I think it first makes sense to think about where design patterns, occur in the design development process. So if you think about the development aspects, there are kind of 2 phases, logical phases, or analysis, and there's design. And then analysis, what we're really trying to do is specify what we consider to be the essential properties of the functional correctness of the system. What does it have to be correct? Design, on the other hand, is really about picking a particular solution. And the reason why we pick one solution or another solution is it optimizes some set of criteria we consider important. These criteria might be things like it's as simple as possible, we save time to market, performance is good, either in the average case or the worst possible case. Predictability is, we have predictability of performance. It's easy to ensure schedulability, that is the ability to meet deadlines and timeliness criteria. Minimize resource or maximize resource usage, utilization, minimize times to do things like thread switching, context switching, robustness, and so on. Safety, reliability, security, and so on. So these are just some of these kinds of criteria that you want to optimize. And the reason why this is relevant is because different patterns use different approaches, different technologies, different attacks to solve these problems, and they have different pros and cons. And the patterns differ in terms of their selection criteria. on the kinds of things that they optimize. But they also differ in the kinds of things that they de-optimize. Whenever you optimize one aspect, you de-optimize something else. You may get better performance, but it takes more memory, for example. And so we have to pick a set of patterns to form a good design. And by good design means that we get the performance optimizations and the product optimizations we want at a cost that we're willing to pay, right? That's what we call a good design. Now, I think that there are different levels of design. Okay, so in analysis, you do something which is functionally correct, okay? But it's not optimized, right? But it's functionally does what we need it to do. That's what I consider to be the analysis model. And then we have system-wide optimization, and that's what we call architecture. Architecture is really a sum of a bunch of design patterns in different areas of design. In the harmony process, of which I'm the author, we have kind of 5 key areas of design. We've got things like subsystem and component architecture. We've got deployment architecture, which is the arrangement of different engineering disciplines like software, mechanical, electronics, optical, nuclear, chemical, and so on, and allocation responsibilities into that deployment architecture. And then also how the different aspects integrate. How do you call the software from the electronics or vice versa, for example. Then we've got concurrency and resource model. How do we optimize the various tasks and threads and sharing resources robustly across those task threads? We've got the distribution architecture, how we distribute software across different address nodes and allow them to collaborate effectively. And finally, we've got the dependability architecture, which is concerned about three pillars of dependability, which are safety, freedom from harm, reliability, which is a measure of the availability of resources and the delivery of services, and then the security, which is protection against intrusion, interference, or theft. Right. So that's architecture. And so we have patterns in architecture in each one of those different areas of architecture, and together they form our system architecture. So at the collaboration level, this is where the Gang of Four book, we'll talk about in a second, really focuses, where we have collaboration of software elements, classes and objects, or functions and data structures collaborating together to achieve some sort of system-wide or larger scale functionality. We call that collaboration, or it used to be called mechanistic design. And lastly, we've got what I consider detailed design, which is the optimization of individual small pieces. These can be functions, algorithms, data structures, classes, and so on. So scope and level of depth are different in each one of these different levels. And there are patterns at these different levels to optimize our system. So what actually is a design pattern? A design pattern is defined to be a generalized solution to a commonly occurring problem. So what that means is that we solve a number of problems using a similar technique. We say, you know what, we just use the same kind of approach in all these different specific solutions. Let's abstract away the approach and remove all the context-specific information, and that abstraction is called a pattern. Okay? So we'll use UML to represent the patterns. I know lots of people don't use, you're doing C, don't use UML, but it's a good way to at least visualize it, even if you're not using UML in your design work. Although you can use UML, and we'll talk about how you can do that a little bit later. Another way to think about design patterns is their parameterized collaborations. So we've got a collaboration, a set of software elements that they have roles. And some of these roles in this collaboration are really placeholders for specific things from your actual analysis model that you plug in. Those are the parameters. So you take your element from your analysis model and plug it into the pattern, and you instantiate the pattern for that particular context. Okay? So there are two kinds of objects, I guess. There's these glue objects that kind of perform the pattern optimization functionality. And then these formal parameters with the elements from your analysis model that you plug in to glue together to come up with the design model. Okay? And so the important aspects of patterns are when it applies, replicability, what has to be true or what you're assuming is true in order to apply the pattern, what it optimizes. So why would I want to use this pattern? Because it optimizes performance or worst case performance or repeatability or reusability or whatever characteristic you want. Then there's the description of the solution itself. Normally both the structural and behavioral aspects of the solution are shown. And then I think even most important here are the consequences, the pros and cons, the things that it optimizes and the things that it de-optimizes. So you can understand which patterns might be better for your particular context. So, of course, there's a classic text published in 1995 by the Gang of Four, Gamma, Hine, Johnson, and DeSalle. And they identified three kind of categories of patterns here. And these are really are considered by and large IT patterns. So not embedded patterns, but more general software IT patterns. Doesn't mean they can't be applied, although sometimes it's a bit of a challenge to see how. But just general kind of software patterns. And then one of the books I wrote on patterns, this Design Patterns in C, we do have those kinds of patterns, but we also add things like state behavioral patterns, ways of organizing state machines to achieve certain kinds of performance benefits, distribution, dependability, deployment, concurrency, resource. So I have some additional types of patterns that I find useful in development of real-time and embedded systems. So, quick example. So here we've got an analysis model. We've got a train going down a track, and it's got an optical sensor. So we shine a light at the wheel as it turns, and we've got a little hash mark on the wheel, and a photoreceptor which receives the return light from the wheel as it spins. And when it dips in reflection, because the hash mark goes by, we can time that, and because we know the size of the wheel, we can then do the math and produce the velocity of the train. So we've got this AD converter, optical sensor, and high-pass filter, and that results in train speed, shown here as a double. And then there are a couple different kinds of clients for this. There's a textual view. So you can imagine a train with 100 cars. You've got a bunch of text views in each car that says how fast the train's going. All right. And you've got a speed controller, so you're doing engine control, so you want to maybe have an autopilot for your speed. To do that, you have to know what the outcome is, because you can adjust the engine output to match the outcome. Okay, so now we want to do some optimizations. So first of all, I want to be able to efficiently update the speed controller. So right now, as it's kind of displayed here, text view has to somehow get train speed. Well, one way would be that the text view asks for the train speed, or the speed controller asks for the test view. Ask for the train speed. So that works, but it doesn't really know when it changes. You might be going for 4 hours in cross Kansas at exactly the same speed, right? So you wasted all this bus bandwidth asking for data that didn't change. That's one approach. Another approach would be that I can use a kind of client-server architecture where the train speed doesn't know who its clients are, or knows who its clients are rather, and so it can, when the data changes, it can tell all of its clients, the text views and speed controllers, what the data is. But that breaks the basic client-server architecture, where the server shouldn't know the clients, because then whenever I add a new client, you got to modify the server. Right? So what can we do about that? Another thing we want to optimize is that bus bandwidth, so that we minimize the traffic on the bus to only when it's needed, right? So if we need to have the data sent across, send it across. So if only there was a pattern, some way of solving this problem that met that need. Well, it turns out that there is. Okay, so the optimization criteria we're looking for is optimize the bus bandwidth, simplify addition, removal of clients as you change the cars that are attached to the train, and enhance our ability to maintain the system. So by looking at the literature, we say, the observer pattern solves that problem. A pattern is structured like this. We've got these blue objects, such as the abstract subject. It's the element that has information that somebody else cares about. And so it manages that, and it's got a list of people who care. So it's got services for subscribing to it, and it's basically to send, in some sense, logical sense, the address of the client. Contact me at this address when the data changes. For example, when some policy criteria is met. And that results in a notification handle. So notification handle is basically the address to talk back to that client. And it can be in the same address space, or it could use a TCP IP addressing. However you decide to do the addressing, notification handle allows you to add clients to the subscribe method and unsubscribe them later to the unsubscribe method. Right? So those are the kind of the glue elements. And then your particular elements from your analysis model form these formal parameters, the concrete subject and the concrete observer. So the pros of this pattern, it maintains the classic client-server approach in terms of the server doesn't know its clients at design times. I don't have to change my design to add a new client. I can do it dynamically at runtime. It's easy to add and remove clients via subscribe and unsubscribe. Timeliness is good because I only send the data when the data changes. And bus usage is minimized because the data is only sent when appropriate. Cons are, well, if your bus is unreliable, data may not arrive. You didn't add a confirmation, data arrive. You could add such confirmations, but that would be an elaboration of the pattern. It does add some complexity of what we had before. So now this is our design model, where we see the elements from both the pattern and from our original model. So optical sensor, high-speed filter, those haven't changed. But train speed is now a subtype of abstract subject, which means that it inherits this subscribe and unsubscribe capability and the ability to manage notification handles. And when it's time to update our subscribers with a notify service, it can walk the destinations and the notification handle list and send them all the messages. So this is now the design optimization. And this is basically what you do when you apply design patterns. First of all, you get a working model where it's functionally correct, and then you figure out which one to optimize, select patterns that optimize the things that you care about, or these kinds of things you don't care so much about, and you apply them, instantiate the pattern, and you come up with a design model. That's how this works. So the reason why we use design patterns is because we want to reuse design solutions. The reuse is not just at the code level, it's also at the design and conceptual level as well. So if we have a solution we've used before, wouldn't we like to use the same kind of solution again because it was effective in some cases, right? Because many of these patterns are well known, it gives us a very powerful vocabulary in which to talk about our designs. I'm using a core architecture using time-driven multiplexing concurrency. It says a lot about how your system is wired, right? Because those terms refer to specific patterns that you can go look up and reference. And because we actually have this explicit optimization step, or we can call it design, we can really come up with some, I think, better optimization for our systems because we're explicitly thinking about optimizations. And our designs are more understandable because these, again, these patterns are well documented. So, a big problem I do see is that people optimize systems before they even run. And then getting them to work is a real problem because you've got to get the functionality right and do the optimizations at the same time. In my experience, it's much better to get it functionally correct and then tweak in optimizations than it is to try to get it all working at once. Kind of divide and conquer approach. In my experience, the last 38 years has been much more effective. So let's talk about how to apply design patterns. First of all, we start off with we construct this analysis model that verifiably meets functional requirements. By verifiably means I can test it. It runs, it generates code, whether I write the code by pushing a button in Rhapsody or I write the code in Emacs, I don't care. You know, it's verifiable, yes, that is functionally correct. This is typically not optimized, but it needs to be correct. And if you're going to optimize for anything, optimize for simplicity at this point. Okay? The next step is you identify some set of criteria. Normally it's like 3 to 8, that kind of time frame, that kind of range. These criteria. These are also known as measures of effectiveness. And it could be, you know, heat, weight, power consumption, worst case performance, average performance, memory usage, you know, whatever is important to you, right? Predictability of time use, another common one. Now, not all of these criteria are equally important. Could be that we've got to have something which is really, really fast. And we want to optimize memory too, but it's not as important. So you typically rank these, and what most people do is they rank them on a range of 1 to lowest to 10 to highest. Some people normalize the ranking such that the sum is equal to 10. If you want, I don't use that approach myself, but if you want to use that approach, that can be done too. Right? And so here are the criteria. We've arranged our execution efficiency. We said that's pretty important. That's a 7. Maintainability is a 5. Runtime flexibility is a 4. Memory usage is a 7. So those are our criteria in the case that we're talking about. And then we do what we call like a trade study or analysis, where we look at our different design alternatives. So I think about this in terms of a kind of spreadsheet template, even if I'm just doing it kind of mentally. But I like to actually draw this out because sometimes the optimal solution isn't obvious. So here what we've got the rows as different solutions. So we've got in our particular case we talked about before, a client-server architecture, a push data architecture, and a observer pattern. And then the columns are these different design criteria: execution efficiency, maintainability, runtime flexibility, and memory usage. We've got weights. That's a measure of the importance or significance of that criteria. Execution efficiency was a 7, whereas maintainability was a 5. The number in the cell is the degree to which this solution optimizes that criteria. So the client server optimizes execution efficiency to the level of 3. And again, these numbers are also normalized between 1 and 10 typically. Client server optimizes maintainability to a 7, runtime flexibility to 8, and memory usage to a 5, and so on. So then we compute what's called the total weighted score, right, as the sum of the cross product of the values. So for client server, it's 3 times 7 plus 7 times 5 plus 8 times 4 plus 5 times 7. Okay. So we do that kind of weighted sum. And that gives you a measure of how good this solution optimizes the set of criteria according to how important those criteria are. And the solution with the highest score is, by this analysis, the best solution, because you've looked at it. So once we've selected the patterns we want to use, it can be multiple patterns or just one pattern, we add in the design pattern, and we substitute the analysis elements for these formal parameters in the pattern. And we add these glue elements to orchestrate their collaboration. And there's maybe some refactoring to remove stuff around, particular relations between elements to do that. So there's a little bit of refactoring that goes on when you apply patterns. Not a huge deal, but it is some work. And then we want to do two kinds of verification. Remember how I said it works? The analysis model works, it's verifiably correct? Well, we want to make sure we didn't break it. So we have to then apply these test cases we had before to verify, yeah, it still works, all right? That what worked before continues to work now. And so that's one thing we want to do, is verify that we didn't break it functionally. The other thing we want to verify is we did this design pattern application for a reason. We wanted to optimize criteria. Did we optimize it enough? Some of these may be difficult to assess quantitatively. You just have to look and say, yeah, I think that's maintainable. Other ones you can actually run and measure. You can measure performance, you can memory, so you can measure memory size. And did you meet all of your goals for this pattern? If not, then you might add additional patterns on it to tweak it. You might rip that pattern out and use a different pattern, right? But the goal here is to achieve your design criteria. So let's look at a quick example. So here we've got a medical monitoring device. So you've got an ECG module that producing data from a lead pair. And it sends data into this time marked data queue, TDM queue. That's a queue of data. And you've got a lot of different, and you see it holds a set of queue size of these TDM data. So you've got maybe 1,000, 2,000, 10,000 elements, something like that. And you've got a number of clients. A waveform display pulls that data out to display, to scale and display it. Histogram pulls it out to kind of summarize it. QRS detector looks for interesting events in the waveform stream that indicate the heartbeats. And the arrhythmia detector looks for things like elevated ST segment heights and premature atrial contractions and other kinds of abnormalities in the heartbeat. So all these clients. And so we want to use some set of criteria. And so in this case, we're using the same set of criteria: execution efficiency, maintainability, flexibility, and memory usage in this particular case. So we can, again, use a client server where the server stores data, but the clients then request the data as needed, push it out where the server knows about the clients, push out the data, or the observer pattern where they register for the timely updates and they deregister when they no longer want them. Right? So that's, again, the solutions we looked at before. And here we did our analysis. That looks similar because that's where I took the snapshot from. To do this analysis, we see that observer pattern was the best in this particular case. So then we update it. So now we see that the TDM is a kind of abstract subject. So that comes from our pattern library. And because it's a subtype, it means it inherits those properties. It inherits subscribe, unsubscribe, maintainability. Now, okay, you're talking about doing this in C. How do you do that inherit thing in C? We'll talk about that in just a moment. There's a few ways. You can certainly modify the coding directly, or you can actually do inheritance with some simple kind of implementation patterns, and we'll talk about those in just a minute. We also see that the various clients here are types of abstract observers, right? And we see we've also added this notification handle, and in this case as a linked list. So we can walk this linked list to find all of our notification handles. Right? So again, it's just a very simple modification to an analysis system to get certain kinds of behavioral and performance optimizations. Okay, so what's special about embedded systems? Well, embedded systems are like normal software, except I think in some ways harder because we're constrained. Lots of times we have resource constraints because whenever you embed the software and you ship it with the system, there's a cost per shipped system, and they're always trying to minimize that cost. It's particularly true in like automotive, for example. We want to save 10 cents on a part because you ship 10 million of these parts, and well, that's real money. So they try to save and use absolute minimum amount of memory. You want to use the smallest kind of processor, the slowest processor you can get away with. So they're trying to really limit the resources because it ends up in a cost per shipped item. It's not something you typically worry about in the IT space, right? So you have a little memory. You might have a bare bones real-time operating system with not a lot of services, or maybe no OS at all. Most systems are implemented in C language because of these kinds of reasons, right? 80–90% of embedded systems are still done in C. Having said that, predictability and timeliness are often crucial. I don't know about you, but when I get on an airplane, the last thing I want to hear the pilot say when he comes on is, "Oh my God, is there a programmer on board?" Right? I hate when that happens. Timeliness, predictability of performance are very essential in medical and telecom and aerospace and automotive and so on. So these things are really critical to success in many, many environments. And often many of these systems have high dependability. You're expected to, you start them up once and they run for years. It's not necessarily okay to just reboot your car as you're driving it down the road. That's maybe not okay in the freeway, right? So high dependability is a crucial thing for many of these systems, not all, but many. Right? And we would like to be able to use design patterns to kind of reuse effective solutions given the constraints and the fact that we live with all these resource constraints. So this next section, we're going to talk about some design patterns for embedded systems. Certainly not all. There are hundreds. Certainly just a few of them to give you an idea. Before we do that, Mark, are there any questions that people have to be answered?
No questions have come up in the queue, but before we conclude that, I want to go ahead and invite any attendees to submit a question that I can read to Bruce right now. And while we wait for any potential questions to come in, I just want to remind all the attendees that this webinar is being recorded and that we're going to archive the recording and the presentation on the new website that we've established effective this year. And you'll notice the URL website address is in the chat window of the session. So if you want to copy and paste that into your browser now, you can do so. If not, it'll also be in my follow-up email. So Bruce, no questions. If you want to continue, that would be great.
All right. So let's talk a little bit about design patterns in C. So there are a lot of books about design patterns. Most of them assume object-oriented languages. So most of them assume Java, C++, C#, Ada in some cases. And they don't assume that you only have this kind of functional language like C. Having said that, there are three ways of implementing patterns in C. Some patterns fundamentally assume object orientation, so they're hard to implement unless you use one of these approaches. Some of them don't, right? So there are three styles. We'll talk about each one. File-based is basically just kind of standard C, the C file, each file kind of approach. And we can represent that in UML in a very straightforward way using file as a concept. But it's all just kind of vanilla KNRC, right? Then there's object-based. So object-based really focuses on the identification of objects in our system, but it's not object-oriented. What that means is we identify objects with multiple instances of data sets and functions that work on them, but we don't have inheritance or generalization. So that's a little bit of a departure in thinking from the kind of file-based standard C. Now it does require that you do name mangling of the functions so you can keep track of which functions apply to which these objects. And you typically will use this when you have multiple instances or variables of an element type. So for example, you might have a sensor in a system, temperature sensor, but you've got 20 of them. So you just have multiple instances of that object, sensor, and a set of functions that work on all of them. And we'll talk about how to do that. There are some systems that need a little more complexity than that, and these are object-oriented systems. And the basic idea here is you need to have some way to reference and override functions. So you have a function might mean one thing in an object. If you inherit it and you elaborate that object, you add more stuff to it, the function behavior may change in important ways. But it's still the same function. You want to refer to it the same way. And which subtype you're talking to should be invisible to the client. They shouldn't have to know. It shouldn't break that encapsulation. To do that, I need to have essentially function pointers in some ways. Now, the standard C++ compiler does this by creating what's called a virtual function table. But you don't, and that's certainly an option. You can do that. But a simpler way is just to use function pointers. And we'll talk about how to do that. So this is what looks like representing classes in standard KNRC. The idea is that you take a file, which consists of a .h and .c pair, right? Both the interface and the implementation of that. And in this you have things like variables and event types and functions that you expose, including state machine event receptors. Type def, processor validations, and so on. And you can think of this as a class, right? Typically singletons, this means there's only one of them, but a class. So here we have this class box for test driver, and it's got test 1, EV, reset, and cancel, and test 2, test 3. And you see the stereotype up above. This is GMA file, GMA. It indicates that it's really a representation of just stuff in a C and H file. And it then references the security supervisor file, and that usage reference means that basically it's included in the header file. So I can find it, I can invoke those services, like is digit, is canceled, is reset, unlock the door, and so on. And the security supervisor file then references off to the display file so I can display messages on the screen. And again, so it means that the service display message shows up in the header file so I can invoke that service. The next step up in kind of complexity is this kind of object-based design. And so here we've got this class sensor, and we see that it's really a struct. And the struct contains the filter frequency, the update frequency, how often you update it, the value, and then a pointer to an AD converter, and that's all part of this the structure. So if I want to have multiple instances of variables of these, I just create, sensor 1, which is the type sensor, and sensor 2, which is the type sensor. Right? And the UML view is shown up above in the upper right-hand side. And then you see these services like get filter frequency, set filter frequency, get update frequency, get value, set value, those sorts of things. They're name mangled. And as we took the name of the type of a class, sensor, added an underscore, and we added it to the function operation name. So we can have get value for some other class, and they won't interfere with this because we've mangled the names. Okay? Also notice that get value doesn't need any parameters, right? It just returns the value of the variable value, right? It just returns what's in there. So if the value is 10, get value return 10. But there's nevertheless, if you look in the definition of it, is they've got a const pointer to a thing called me. Why me? I always ask that question, why me? The reason why me is there is because you have multiple instances, or at least potentially multiple instances of this class. And you have to know which instance you're talking about, which data set you're talking about. Is that sensor 1 or is that sensor 2? And the me pointer points to that appropriate struct. So you can get the data from the right element. And the implementation file just provides the implementation of that. That's nothing really magic there. Pretty straightforward stuff. You typically have a constructor destructor. These set up the system or delete the system. You may end up creating, allocating memory. You may have to set initial values. Well, that's what the constructor destructor is all about. So we have this create and destroy operations for that purpose. Object-oriented. So there are a number of ways to do this. I just picked one here. Not quite as flexible as usual. We're using a virtual function table approach, as in C++ did. The original AT&T C-front compiler used output standard C, creating virtual function tables. So certainly can be done. I took a slightly simpler approach to show an alternative. And what I can do here is use what are called function pointers, pointers to functions. So C has a kind of an obscure syntax, I think, for doing the function pointers where you've got the name of the pointer wrapped up in parentheses, followed by the name of the return values and parameters, followed in parentheses. So it's a little complex. But once you've mastered it, it's not that hard. So we've got two function pointers, one which returns of an int and takes no parameters, and one returns a void which takes one parameter, an int. All right, so if there's no parameters, why is there a parameter list? Again, that's for the me pointer. The void star is the me pointer. So now here we've got the struct in the object-oriented sense for the sensor, and we've got same stuff we had before: filter frequency, update frequency, value, and the AD converter pointer. We've also now got pointer to the get filter frequency function and the set filter frequency function. Okay. And in the constructor, one thing we'll do is we'll initialize those pointers to point to our local copies of those functions. Okay. And if we subclass this, then we can repoint those to another rewritten version of that function. So that way we get the ability to re-implement the functions in the subclass based on this new context in which it's operating. All right. So let's look at some patterns. One of these is the hardware adapter pattern. This is like using writing device drivers. It's used when you have an application requires an interface to some sort of physical hardware, but the hardware provides a different interface than the software assumes. So how do you connect them? Well, you create an adapter which adapts the desired interface into the actual interface, so you can actually get the data. So hardware that performs similar functions tend to have similar interfaces, but may not be the same. But sometimes some math has to be done, some work needs to be done to do the conversion, to do the impedance matching between the desired and the actual interfaces. So there can be some work to do that. But what you don't want to have is you want to be able to reuse the existing interfaces without rewriting the software, and you want to use the device drivers you already have for the hardware. So what you do is you create a little adapter that sits between those pieces of software to connect them, right? And the actual interface itself is called the hardware proxy, and we then do this impedance matching to the interface required by the client. So it allows reuse of existing hardware proxies in different applications and for different clients without rewriting the software, which is the main benefit. It does add a little bit of indirection, and so there may be some runtime performance. So this is what the pattern looks like. You see the client, ultimately up on the upper right-hand corner, communicates via an interface, which is realized by this hardware adapter. And the hardware adapter then references off to the actual hardware proxy, which is the actual device driver, to implement those services. And then the hardware proxy talks to the actual piece of hardware itself to perform the actual hardware services, like sense of value, move the motor, or whatever that might be. So let's look at an example of that. Here we've got a gas display and a gas mixer that need to get O2 data. And the data they need are O2 flow and O2 concentration. And there are two different proxies that we have. The Acme O2 sensor proxy, which produces concentration and flow in different units. These have to be converted. So the Acme sensor returns flow in cc's per second times 100, so it's scaled integer. And concentration is in a range of 0 to 100. While what the clients actually want is O2 flow in cc's per minute and concentration in 0 to 100. So there has to be some impedance matching to do there. The other interface is this sensor, is this ultimate O2 sensor proxy. And it returns total flow in liters per hour and concentration as a double in the range of 0.000 to 1.000 with 3 digits of accuracy. And so now the implementation of the Gimme O2 flow in Acme O2 adapter versus Ultimate O2 adapter are going to be different because they have to do different kinds of impedance matching to match those interfaces. And so this shows that the upper one is the Acme O2 adapter. We see that, for example, to give me the O2 flow, takes the get O2 flow, multiplies it times 60, and then divides that by 100 to return to the right units. Down below, we see the Gimme O2 flow for the Ultimate adapter, gets total flow, and converts it to the right kind of units, and then uses the concentration to determine what portion of that total flow is oxygen. Another pattern I use a lot in complex control systems, particularly robotics, is Mediator pattern. Mediator pattern is when you want to manage a bunch of different elements in coordinated and well-defined ways. But those well-defined ways might still be complex. Now you could arguably have all these elements kind of talk to each other and have a group meeting therapy session about it, but often it's useful to have a mediator which takes this high-level task and allocates those tasks in a sequenced fashion to smaller elements to perform the work. And that's what the mediator basically does. It controls system actuators or other devices to achieve coordinated movement, for example, in a robot, right? Or coordinated firing of thrusters in a spaceship, for example, spacecraft. So we have a mediator class coordinates the system to achieve the desired overall effect. It has multiple what are called specific collaborators, a set of elements that we just meant to coordinate. So it doesn't require direct coupling of the devices to each other, just to this mediator, so it simplifies and reduces the complexity of interaction among all the elements in your system. However, there are cases where time delays can be a problem because everything's going through this mediator. And so when that's true, and you need to have high fidelity feedback, you may have to have some additional interaction of the elements directly to coordinate the action because there isn't enough time to deal with the response. The pattern itself is perhaps unrevealing. You've got a mediator with a set of specific collaborators, star means 0 or more, and each collaborator implements an interface, which then can send information typically back to the mediator, closed loop control. So here's the example. Well, we've got this robot arm manager, and it's going to control 4 rotating arm joints, 2 sliding arm joints, and 1 grasping manipulator at the end of the robot arm. And these are the interfaces that are supported by those elements, the eye rolling joint, eye sliding joint interfaces. And the other thing on this is that we have this notion of an action. An action is a position of each one of those various joints elements, each one of those specific collaborators. And the idea is that we have a command to go grasp something at some location. We will compute a trajectory as a series of positions and independently command each of those arm joints to those various positions. This allows us to do a trajectory, for example, that doesn't put the robot arm through the middle of the operator's head, because they hate that, right? So that's the idea, is that the robot arm manager has this task of managing movement of the robot in 3-dimensional space where some areas may either be suboptimal or may be prohibited. And it does this in the compute trajectory task operation. So this defines the behavior for the mediator grab at operation, where we initialize it, we 0 it, then we do call a compute trajectory, and then if status is 0, then we basically, it's not achieved. You can't get there from here. The number of steps is 0. You can't get there from here. Otherwise, you have a number of steps. And then as we go to execute step, we execute each action position 1 step at a time, and then go to the next step until we're finally done. So here is our source code for this robot arm manager class. And we see it's got a current step, the number of steps, and it's got links off to the grasp manipulator. It's got an array of robot arms, it's got an array of sliding arms, and it's got an array of actions up to 100, okay, 101, from 0 to 99 actions, I guess. And then you've got a status, which is how we're doing on the way. So with an action, we see that is just a simple struct. So again, this is a class where basically the data is the point of the class. So you've got the amount of force of the manipulator, whether it's open or not, or the degree of openness, and position of the various other joints in the robot arm. And then as we do the grasp at, we implement this approach. So we start up, we 0 it, we do a compute trajectory, and then we go through step by step until we walk basically through all the steps. And every step we return, if we get the status, as long as the status is okay, we continue. If we get a point where status returns is bad, then we stop. And then when we look at the execute step operation, we, for example, will take the action of the current step, we get the action value, we tell, in this case, the robot arm joint 1 to go move to that position, we get the status back to make sure we're able to achieve that. So the idea is that robot arm joint may return a problem. I wasn't able to achieve it, I'm broken, I've lost high electrical power to my motor, I've lost hydraulic force, whatever the case may be, it will return an error status. And if the status returns that there's a problem, then we can terminate. Otherwise, you go to the next step. And then it continues. So I don't know, that's particularly interesting. You can look at it more in the slides for the webcast after the fact. So those are just a few of the patterns. If you look in the design patterns book from Embedded Systems in C, there's, I don't know, 30, 40, 50 patterns, something like that in there. Design patterns book by Bagama et al. Is a very good book. It's not UML because it actually came out in '95, which is the same year that UML 1.0 came out. So they made up their own graphical language to show stuff, and all the examples are in Java. It's not a terrible thing, but if you're a C programmer, you should know that. There's a series of books by Frank Bushman and others called the Pattern-Oriented Software Architecture, and there are different specializations. Some are distribution patterns, some focus on security. There's a bunch of books in the series, and it's highly recommended. And there's also a book called Real-Time Design Patterns below that that I wrote, and it's basically architectural patterns focused around these kind of 5 views of architecture that I discussed before. So with that, I'd like to please control back to Mark and answer any questions you might have come up with.
Thanks, Bruce. Excellent presentation. We really appreciate that. So again, attendees, the panel is open. I've answered a lot of questions already directly with you folks. I was expecting a lot of questions, so I was there for taking care of the questions while Bruce was talking. Bruce, a question has just rolled in here. It says, you mentioned that there are additional types of pattern types in the embedded world compared to GOF. Does SysML better support this pattern landscape?
Okay, so UML and SysML are languages. They're graphical languages, but they're built on a model architecture. So they are the language that we might capture patterns in, but they are not the patterns themselves. Okay, so you can build up a pattern library in SysML, or you can build up a pattern library in UML, and to a large degree they would be consistent between each other. So, for example, if you look in the design patterns book, real-time design patterns book on the bottom line of the slide, those patterns apply equally well in UML and in SysML. Now, SysML does add some extensions. For example, it adds continuous behavior in activity diagrams with the notion of streamed flows and continuous flows. It adds parametric diagrams doing parametric analysis. And so you can do some patterns around those kind of extensions. But otherwise, SysML, 80% of SysML is UML. And so there's a huge correspondence between the two.
Okay, great. If you'd like to ask a question, I can read it immediately to Bruce, and we'll wait for that to come in here. Bruce, I think that's going to be it for the questions. So is there anything you'd like to say before we wrap up the webinar?
Patterns rock. I really like patterns because it gives me a kind of formalized way of thinking about and optimizing my designs and really capturing, what was my intent. Too many designs, I think, are done kind of willy-nilly without a deep regard for what I was actually trying to accomplish with the design. For example, I do a lot of consulting in various companies, and one of the things I've dealt with a lot lately is security in cybersecurity and embedded systems. And a lot of companies, the approach they give to security, the thought process is security, yeah, I need me some of that. And that's the level of depth that it gives. And I think this allows you to really think about, analyze what we're trying to optimize and what kind of benefits we specifically get from the optimization of design patterns and come up with much, much better designs. So I really encourage people who don't have much experience with patterns to look at some of the literature out there. There's, again, do a Google search. There's all kinds of papers. I've written some myself. There's all kinds of presentations. Design patterns are really a great way to implement optimized designs.
Bruce, another question just rolled in. I'm not sure how we can answer it, but I'm going to ask it anyways, and that is, how do you get close to executable UML without expensive software? And he had a simplet template CH files. Is that something that you can, I think, reasonably answer?
Yeah, sure. So there's a class of models called computable models. And a subclass of those are executable models. So thermodynamics, for example, is computable, but not necessarily executable, because it's bidirectional. Your execution assumes that you have a series of steps to a known specific outcome. So you have to pick one side and say, this is my dependent variable, this part is my independent variable, before you can make something executable. So having said that, UML has some part, and this is true with SysML and UML, both, equally true for both of them, has parts which are formal and parts which are less formal. Use cases, for example, are less formal. But you can construct models that are formally specified in terms of state machines, in terms of activity diagrams, detailed behavioral models, sequence diagrams, and so on. These are well-formed, precise statements. Now, there's a couple of ways you can do this execution. You can do simulation, and you can do code generation and execution. From a system engineering standpoint, it doesn't matter what you do. The fact that it's executing is the point. You wouldn't reuse the code you generated to do that if you're doing a tool like Rhapsody. You would, but you would use the result of the fact that you can execute it. So whether you're doing a translator into a code that's then compiled and run it, or if you did something like token-based execution in a virtual machine, really kind of from the execution standpoint of the model doesn't matter. Where it does matter is if I'm doing UML for software, such as embedded software. Then I want to use and deploy that code on the actual targets, and you can do that. But that's not the only way to get an executable model. You can execute a model in a variety of ways. Like I say, you can pass tokens around, for example, and there are some tools that do that. So what Rhapsody does, Rhapsody generates code in a number of different languages. And for system engineering, we still generate code, but we, as a system engineer, they don't care about the fact that it's code. It executes, and that's what they care about. And they can visualize that execution at the UML concept. So I can look at the state machine. I can see states get colored as they're in the current state, and as I see transitions fire, that gets colored differently. Sequence diagrams will be drawn dynamically as the elements in my design collaborate. That's what I care about when I'm executing at the model level. And whether I do that with code or some other means really kind of doesn't matter.
Bruce, you mentioned singleton. Is there any benefit in that specifically for code generation, C code specifically?
The benefit is, the singleton, is you basically prevented from creating extra instances of it, right? And so there isn't any question about memory loss because you've got all these dangling classes around. If you always want to refer to, like, for example, an error handler or a display device or something where you've got singletons. So I don't know of any real downsides to it for that. It's just basically the idea of a singleton is in a singleton itself, you basically prohibit creating new instances of singletons. So the new instance, when you say give me a new one of these, you basically just return a pointer to the existing one, right? So everything is class-wide, not instance-wide. So the difference between, again, the idea of class-wide is that a class-wide value, for example, is a value, a specific value is known to all instances, as opposed to an object-wide variable with a value may differ between instances for the same variable, right? So I don't know of any problem doing singletons. I've used singletons in embedded designs in C without problem.
Okay, great. There's a question that came in, but I'm not really clear. It has to do with enablement of concurrency patterns. Is that something that you can discuss or elaborate on in any way?
Oh, I could give a whole talk on that. So there are a number of areas of concurrency where we focus on in terms of patterns. How do I schedule threads? How do I identify what good threads are? How do I share resources across threads? How do I guarantee schedulability? How do I avoid things like deadlock and live lock, right? As there are patterns in each one of those areas. So if you look at, in fact, there's a section of the design patterns book that I wrote on that topic, in the real-time design, the one at the bottom of the screen. on that topic. There are, I can say, like 4 or 5 separate areas within the concept of concurrency where you can apply patterns. So your concurrency architecture is you'll pick one or more means of identifying and classifying your threads. You'll identify how do you want to schedule them. That is, if I have multiple tasks ready to run, how they decide they should run. Whether it can be priority-based preemption, it can be round robin, it can be cyclic executive, TDMA. There's a bunch of approaches, right? And then how do I share resources? I can use things like critical regions. I can use things like semaphores. I can use queuing. You know, so there are ways that I can share resources across that. So all of these areas have solutions that have, again, pros and cons. You can pick which ones make the most sense. There are solutions around deadlock, for example, avoiding deadlock. So, for example, a deadlock requires kind of 4 conditions. I don't want to go down that rabbit hole too deeply. There are 4 conditions required for deadlock, and you can prevent deadlock by preventing any of these conditions. So one solution is simultaneous locking. So I lock all the resources at once, or I lock none of them at all. Okay? And you can write software to manage that, to make sure that it succeeds. So you avoid deadlock in that. It breaks one of the rules that's required for deadlock. Another one is called ordered locking, where I give every resource I want to lock a resource number. And I have a rule that says you can only lock resources whose ID is greater than resources you currently have locked. And that prevents the recursive rule required for deadlock, right? So there are different solutions with different, again, pros and cons. So yeah, that's a rich topic. And I have a whole set of materials on just that.
Okay, great. A lot of thanks have come in here. We have a number of students that are thanking you, Bruce, that they've made comments that they have a number of your books and they've really enjoyed them. So I thought I'd just make that comment. Okay, the panel's open, attendees. Feel free to ask a question. I can go ahead and read it to Bruce immediately. Nope, I think it's going to be it. I think we can wrap up. So we'll conclude. Again, if you have any further questions, you can get Bruce's presentation in the handout section of the control panel, or you can wait for my automated email that will include the link on where the recording and the presentation will be archived. And Bruce, I believe you put your contact information on the cover page, and I assume that it's okay for individuals to reach out to you separately. So feel free to do that, attendees. So with that said, we've concluded the webinar. Everyone have a great weekend. I look forward to seeing you on future Enlightenment Series webinars. And Bruce, thank you again. So with that said, we've concluded. Take care all, and goodbye.